Slide 1. Dear Chairman, dear colleagues, and guests. I'm an automatic text reader, and I'll present to your attention the improvement of thermopile sensor performance for determination of the physiological condition of cucumbers, with authors Myroslav Vasilev and Zlatan Zlatev. Slide 2. Drought and high temperatures are the two abiotic stressors that determine the magnitude of damage to cucumber crops. They lead to disruption of the normal water content in plants, and hence to their ability to absorb nutrients. As a result, plant growth, photosynthesis, and development are slowed down. Leaf temperature is a valuable indicator of the physiological status of plants, corresponding to both biotic and abiotic stressors. An effective method for determining changes in leaf temperature is thermography. It can ensure the application of automated, precise and sustainable agriculture. At the present stage of development of science and technology, wireless sensor networks offer theoretical and practical challenges related to their application capabilities. Each area of application of sensors and sensor networks is associated with huge data streams generated by the sensors. The disadvantage of thermal cameras is that images with dimensions over 320 by 240 pixels are obtained. This makes them unsuitable for use in wireless sensor network systems. They do not meet the condition of receiving and transmitting small amounts of data over a distance. The solution to this problem is the use of thermopile sensors. They are matrices of thermocouples, measuring 8 by 8 pixels. In order to use such data, they need to be interpolated and scaled. Mathematical apparatus and methods for extracting information from small volume data from sensors are: interpolation, an approach that refers to the determination of intermediate values in the data; compressed sensing, an approach for compressing data with their subsequent facilitated recovery; sampling, an approach that allows sampling of a continuous signal according to the maximum frequency of the signal spectrum. Slide 3. The aim of the present work is to make a comparative analysis and to select appropriate methods for interpolation of data from a thermopile sensor in the analysis of cucumbers in a period of drought. Slide 4. Cucumbers are grown in adapted conditions at a temperature of 30 degrees Celsius and relative humidity 70%. Cucumbers were watered at the beginning of the study period, waited to recover, and then their drought was monitored. Color digital images and those with a thermal imaging camera were taken for a period of 3 days, 72 hours. The thermal images with a resolution of 640 by 480 pixels were obtained with a Blackview BV9800 Pro mobile phone. The thermal sensor is FLIR Leption 2.0, FLIR Systems Incorporated. An IR thermal camera AMG 8833, Adafruit Industries Inc. was used. The sensor has an 8 by 8 pixels matrix using the thermopile measurement method, which is a matrix of thermocouples. The interpolation method is suitable for use in determining intermediate points between the pixels of the image of the captured object obtained with the AMG 8833 thermal sensor. The following interpolation methods are used and compared in the present work. Linear. The interpolated value at a given point is based on the linear interpolation of the values at adjacent points. Nearest neighbor. The interpolated value at a given point is the value at the nearest point. Cubic. Interpolation is based on calculating a cubic curve between points. Modified Makama. The interpolated value at a given point is based on a function of polynomials of degree up to third, estimated using the values of adjacent points. Akama's formula has been modified to avoid data overlap. Spline. Based on cubic spline interpolation. Slide 5. The comparative analysis was made on the basis of the histograms of the thermal images from the thermopile sensor and the thermal camera. Criterions are according to Bityukov et al. and Wang et al. Two hypotheses are accepted. H0, there is no statistically significant difference between the groups. H1, there is a statistically significant difference between the groups. The last criterion used is p-value. If p is less than alpha, the null hypothesis is rejected. All data were processed at a level of significance alpha equals 0.05. Slide 6. Once an appropriate interpolation method has been selected, partial least squares regression, PLSR, and principal component regression, PCR, methods have been used. The statistical parameters used to analyze and evaluate the PCR and PLSR results are the coefficient of determination, R², mean square error, MSE, root mean square error, RMSE. Slide 7. Figure 1 shows images obtained with a thermal camera in the area captured by the thermopile sensor. They are applied to the RGB image of cucumber leaves subjected to drought. There is an increase in plant temperature during this process. Slide 8. Figure 2 shows examples using interpolation methods. They are compared to one from a thermal camera obtained in the range of the thermopile sensor. In the linear and nearest methods, the image is pixelated, but to a lesser extent it is the one obtained by the second method. After processing with the other three methods cubic, Makima, and spline, the contours in the image are smooth. Slide 9. Figure 3 shows histograms of images obtained with a thermopile sensor and a thermal camera by linear interpolation of the pixels of the sensor. The data from the two sensor devices are normed in the range 0 to 1 for comparability. At the beginning of the measurements, the histograms show that the pixels from the sensor are grouped in the range 0.1 to 0.2. Those from the thermal camera are in the range 0 to 0.1. This trend continues after 24 hours. Then in the third and fourth measurements, the pixels of the two devices are in close ranges. Slide 10. The highest degree of data overlap in the histograms of the thermopile sensor and the thermal camera was observed using spline interpolation, compared to the other four methods. Again in the first hours, 0 to 24 hours, there are minimal differences in the data, and then, 48 to 72 hours, the histograms have minimal differences. In summary, it can be said that a suitable method for interpolation of data from a thermopile sensor for the purpose of their scaling is spline interpolation, because when using it there is a minimal difference in the histograms of the obtained data for the measured temperature of cucumbers. Slide 11. The spline interpolation method is selected. The scaled data from the thermopile sensor were analyzed by PCR and PLSR methods. The number of principal components and latent variables has been determined, which describe with an accuracy of over 95% the dispersion in the data from the thermo-sensor. Figure 4 shows the result of this analysis. As can be seen from the figure, two principal components and two latent variables describe 95.23% of the variance of the experimental data. Figure 5 shows the PCR and PLSR results from data reduced by two components each. The PCR method stands out, as it shows high values of the coefficient of determination for the whole measurement period. Data obtained by PLSR have a lower predictive power than PCR. The results show that the temperature of cucumber leaves in the period of their drought can be determined with a constant value of the coefficient of determination, 0.81 to 0.85, by means of data from a thermopile sensor, interpolated and scaled by the spline method. Table 3 shows the evaluation results of the obtained models. Detailed analysis shows that PCR-reduced data have a higher predictive power than those obtained with PLSR. Proof of this are the high coefficient of determination and the lower error values. The accuracy of temperature prediction with a thermopile sensor reaches 85% when reducing its data by PCR. Slide 12. The results obtained in the present work complement those of the available literature. Spline interpolation is an effective method for obtaining intermediate points, both transitions to create complex curves, and when creating predictive data models and designing motion trajectories. In the present work, the spline interpolation method has been successfully applied in scaling a data matrix obtained from a thermopile sensor. Thermopile sensor data interpolated by the spline method can be used to assess the condition of crops and in particular cucumbers. The small amount of data and sufficient accuracy of 85% indicate that using a sensor network with AMG 8833 sensors, the recommendations of Kashyap et al. According to the guidelines given by the authors, the monitoring of the condition of agricultural crops is an important parameter in the management of agriculture to obtain accurate data leading to sustainability through precision in agriculture. Of course, thermal sensors, despite their simplicity of operation and the small amount of data received, also have their drawbacks. For example, if the ambient temperature is equal to that of the leaves of plants, measurement with a thermosensor will be ineffective. One of the possible solutions to this problem is to combine the data from the thermosensor with those from a video or colorimetric sensor. Slide 13. In the present work, a comparative analysis is made and a suitable method for interpolation of data from a thermopile sensor in the analysis of cucumbers in a period of drought is selected. The choice of method for interpolation of data from a thermopile sensor affects the accuracy in determining the temperature of cucumber leaves. These results are confirmed by a comparative analysis of 5 different interpolation methods. The analysis of the results revealed that the linear interpolation and the one based on the nearest method are unsuitable for efficient data processing by a thermopile sensor, in comparison with the other interpolation procedures, in the specific conditions of the solved problem. When using these methods, in addition to obtaining a pixelated final image, the obtained data have high error values compared to those of a thermal camera. It has been proven that a suitable method for interpolation of data from a thermosensor for the purpose of their scaling is spline interpolation, because when using it there is a minimal difference in the data from the obtained histograms when measuring the temperature of cucumbers. It was found that the analytical models obtained by the principal component regression describe with sufficient accuracy the relationship between the empirical data from a thermopile sensor and those from a thermal camera with a coefficient of determination 0.85. To approximate the relevant empirical data, the model with the lowest values of errors in its estimation was chosen. The obtained results have the potential to be used in the creation and improvement of sensor networks in precision agriculture. At the next stage of the work, analyses related to the combination of the data from the thermosensor with those from other types of sensor devices such as colorimetric, spectrophotometric, video, ultrasonic, multi, and hyperspectral sensors in the diagnosis of the physiological state of cucumbers are envisaged. More research is needed, including benchmarking with more complex methods of data processing and solving optimization problems, such as the compressed sensing method. Slide 14. Thank you for your attention.